Hello, and welcome to the module on friction, springs, and elasticity. I'm going to start with friction. I have a deck of cards on a plastic surface, and I'm sitting it here and not putting any additional forces on it. The forces on that deck of cards are the normal force that's perpendicular to the box, the weight of the cards, and friction. Friction, pending motion, if they were to slide, would be down the ramp. So what's keeping it in its location right now is the force of static friction. That's friction when something isn't moving and it goes up the plane. I'm gonna replace, so same angle, but I'm gonna replace it with some smooth paper and put my deck of cards here, and we see it slides. That's because there is less friction between the cards and the paper than the cards and the plastic. When the cards are sliding down, there is still friction, but it's the force of kinetic friction. So that's friction that exists when something is moving. So let's look at the equations. So friction, we have two kinds, the static, which again, that's not moving, and kinetic when it's moving. And in both cases, we're gonna calculate the amount of friction by taking the normal multiplied by the coefficient of friction. So in the example I just showed, the plastic with the cards had a bigger coefficient than the paper with the cards because it had a bigger force of friction. Our next concept deals with springs. So we talked about these a little bit in the previous chapter. I have two springs here with me today. Can you see them? This one's really floppy. It has a low force constant. This one's a lot stiffer. It has a higher force constant. So that's something that's kind of like good to keep in mind as we work some of our problems. So let's head over here to look at the equations, and I have a little demo set up for you that involves a mass on a spring. Hooke's law, which we saw in the previous chapter, says that the force for like the restoring force on a spring is negative the spring constant. Remember, if it's really a floppy spring, it's a lower spring constant, times the displacement. And I've put up here the units, forces in newtons, displacements in meters. So our spring constant, or also called our force constant, is gonna be in newtons per meter. K is always a positive value, always a positive value. And that's because the sign on the force and the displacement are always going to be opposite. Okay, so I've set up a little demo here. I've got my mass on a spring and I'm in equilibrium, so we'll call that x naught. I'm in equilibrium. And if I imagine my origin was right here, if I pull this down to here, I now have a negative x position. So a negative x position. So my delta x final minus initial gives me a negative x. I'm gonna let it go, and we see its oscillation. And it goes up to this spot, which if my origin is here, is a positive x. So my delta x final minus initial gives me a positive displacement when it's up here. So putting this together with Hooke's law, when x is positive, F is negative. When it's up here, the force is pushing it to go back down because the spring doesn't want to be compressed. That was equilibrium. And when the mass is down here at a negative displacement, the force is positive because the spring doesn't want to be stretched. It wants to go back up to equilibrium. So that explains these signs and how you should find that they're always opposite each other. All right, this is kind of a weird chapter. It put friction in with springs in with this other topic, elasticity. So elasticity is looking at how solids are deformed. And we're going to primarily look at it, 3 different kinds of deformations. We're going to look at a length deformation. So suppose you had a pillar that was made out of plaster and you wanted to put a really heavy statue on it. When you put that statue on it, the pillar is going to get compressed a little bit. We will also look at a shear modulus. So a shear modulus is when the top of a surface has a force put on it and the whole, let's say, box kind of gets deformed. I have a picture I'll show you in a moment. And a volume deformation is when something gets uniformly compressed or expanded. So think about a stress ball and how we might squish it. That's a volume deformation. So in calculating these, there are quantities that physicists and engineers have come up with called strain and stress. Strain is a ratio of the original length of the object and how much the length changes. So that's a measure of how much it's been strained. If I look at its initial compared to how much it changes, if this is a small number, it doesn't have a lot of strain. If it's a really big number, it would have a lot of strain. And the other quantity that we'll need is stress. And stress is a ratio of the force divided by the area. So the amount of force that's applied divided by the area that it is applied to. So often that's going to be a cross section, which we'll see when we get to problems. So Young's modulus is a value that is the ratio of these 2 ratios, stress divided by strain. And this is unique to material. Unique to material. So we'll do a problem that involves an aluminum column. And this is something that you'll either look up when you do homework problems or you'll be given it in the problem. Quick side note, we do have a new unit. That is a Pascal. A Pascal is the SI unit for pressure, and it is a Newton divided by a meter squared. All right, so let's look at the specialized equations. This one is for the length deformation. So Y, that's Young's modulus. That's the thing you're either given or you're going to look up. Force is the amount of force that you are applying to the length. Maybe you're stretching it, as we'll do in one problem. Maybe you're compressing it, but it's whatever the force is that you apply. The area is the area to which the force is applied. So often it's going to be a cross-sectional area. And L naught is the initial length. This next one is a shearing deformation. So I have an example here of like a picture that shows how we might think of this. Let's suppose I'm looking at a book and the side spine of it. Are we close enough that we can see the letters on here? So we're looking at a side view of a book where this is the height of the book. So kind of the thickness of the book. If I were to put my hand on the top cover of the book and push, I could apply a force to the top cover of the book, and the area in this case would be the area to which I'm applying it, so the area of that top cover. And what will happen is the top cover will move to the right, and it will be further to the right than the bottom cover. So this delta X here is how much the top cover has been displaced from its original position. So it's important to kind of know what these are when it comes to putting it into the equation. So this delta X is how far the top has been displaced from its original location. S is the shearing constant that you're going to look up depending on material. Force obviously it's the force that we're applying. The area is going to be the area of the palm or the area of the book, and h is the original height of the object, or in this case, a book. And the last one here is volume deformations. Again, initial volume, the area that we're applying it to, so it's often going to be like a surface area of a cube or a sphere, all on your equation sheet. The force, and then this is called the bulk modulus. Again, you probably guessed it, it's something that you look up, and it is a constant for the material. I hope this has been a good introduction to this chapter. Next, we'll start working some problems.